Right, so today we're going to be doing galvanic cells and how to answer some certain questions about galvanic cells. Right, so before we start, what you're going to need to know is definitions of reduction and oxidation, definitions of oxidant and reductant, and mechanics of a galvanic cell. Okay, what does that mean? It just means that you really generally should know what's an electrode, what's an anode, what's a cathode, what's the purpose of a salt bridge, what do we mean by electron flow through the external circuit, things like that. Alright, so the general ideas of galvanic cells, and then this will just be a video on how to really just get all of the specifics out of a particular galvanic cell question. Alright, so galvanic cells, this is just a recap of how galvanic cells work. They produce electricity because certain chemicals have differences in potential energies. So this electricity is only created because you're separating the oxidation and reduction reactions from each other and forcing the electrons to flow through the external cell. You've got your half cells connected by the external circuit and the salt bridge. You should know what the salt bridge is for, to balance out the charges. The half cells that we're talking about now contain the oxidant and reductant pairs. Okay, and so when they're connected, the electrons flow from one to another, so on and so forth. Okay. So this is the important part. To determine which chemicals pull electrons from the other, we can use experimental data that's already been conducted to predict how the reaction will occur. To predict how the reaction will occur. Good English, Mr. Lim. So, the standard reduction potential table, the SRPT, will help us predict a number of things, and these are the things that will be asked of you in tests and exams. Okay, which way are the electrons flowing? Which electrode is the anode and which is the cathode? Which way are the positive and negative ions flowing? What are the oxidation and reduction half equations, and what is the voltage of the cell? Okay, and to do that, we're going to have to follow a whole bunch of steps here. Okay, so we're going to have to do all of these here, which we're going to go through via some examples instead of having to just read them all out. Okay, so some of the examples are here, and so we're going to do the first one, which is the silver half cell and the nickel half cell. So let's go to this. Alright, first of all, you're going to draw out the two half cells. Okie dokie. So you need a half cell here and a half cell here. Okay. This will be the nickel, this will be the silver. Right, what's this missing? It's missing a salt bridge. It's also missing the ions here. Okay, how do I know that this is a silver 1+ and this is a nickel 2+? Alright, number one, I have been memorizing the ions table that has been passed out. Also, if you really are confused, you can use the standard reduction potential table to let you know, okay, when here's the silver one, it's a 1+, here's the nickel one, it's a 2+. Okay, so we have our our galvanic cell here. Let's go look at the steps. Okay, so step number one is to identify the reactants on the standard reduction potential table, and we did that kind of because we already have squared them. And so I know that here is my silver ions, here's my silver, here's my nickel ions, here's my nickel. Alright, what's the next step? The next step is to identify the oxidant and the reductant. Now the oxidant is always going to be on the top left and the reductant is always going to be on the bottom right. Now this top left, bottom right configuration is very important for galvanic cells only. So for galvanic cells, you've always got a top left and bottom right configuration for what reaction is actually going to occur. So let's have a look. What's on my top left, what's on my bottom right? Top left, I got the silver ions. On the bottom right, I've got my nickel solid. Okay, so my silver ions are my oxidant, and the nickel solid is the reductant. Alright, if the silver is the oxidant, it will undergo reduction. And the nickel is the reductant, it will undergo oxidation. Leo the Lion says Gur, oxidation is the loss of electrons, and this is the gain of electrons. Okay, so we've identified the oxidant, the reductant, because of their position on the standard reduction potential table. We've identified that, okay then, because this is the oxidant, reduction is going to occur. It's going to gain electrons. The oxidation is going to occur on this side. It's going to lose electrons. If this loses electrons, this gains electrons. Which way are the electrons flowing? Okay, they're going to be lost from here and gained over there, so the electrons are going to be flowing this way. Okay, is that clockwise or anti-clockwise? That is anti-clockwise. Okay, so just make sure that you recognize which way a clock goes. All right, let's have a look at the next step. So we've just determined the electron flow, which is kind of useful. Now we're going to determine the location of oxidation and reduction. Oh wow, we did that already. That's useful. Oxidation occurs over here, reduction occurs over here. Right, so therefore we can determine the identity of the anode and the cathode. So anode is where the oxidation occurs, always, okay? And cathode is where the reduction occurs. So the anode is where the oxidation occurs. So this here is the anode. Okay, notice how I'm pointing to the actual metal object connected to the external circuit dipped in the solution. That nickel piece of metal is the anode, and this silver here is the cathode. Please take note that the entire half cell is not the anode, only this part here is the anode. Only that part there is the cathode. Okay, so I've identified the anode and the cathode here. Alright, what's next? Once I've identified the anode and the cathode, we have to work out the directional flow of ions through the salt bridge. Okay, so the positive ions flow towards the cathode and the negative ions flow towards the anode. So let's have a look here. The positive ions flow towards the cathode. Okay, so the cathode is here. Another way of thinking is that's the positive ions, they flow that way. Another way of thinking about it is that the positive ions will always follow the direction of the electrons, because the electrons are coming over here, making this more negative. If this is more negative, the whole purpose of the salt bridge is to equalize its charge, which means that the positive ions must go over there to make this one less negative or make it more neutral. Alright, if the positive ions go that way, the negative ions go the other way. Alright. So that's your flow of ions through the salt bridge. Okay. Now we're going to determine the oxidation and reduction half equations. So the oxidation at the anode is the reductant reaction backwards on the SRPT. So the oxidation at the anode is the reductant equation, which is the nickel, this is the bottom right, going backwards. Okay, so the nickel solid turns into nickel 2 plus aqueous. So the nickel solid goes to nickel 2 plus aqueous, plus 2 electrons. Okay? On the other side, the reduction equation is the reduction equation at the cathode is the oxidant reaction forwards on the SRPT. So here is our oxidant, the Ag+. It's the reduction reaction forward on the standard reduction potential table. So silver ions turn to silver solid. Silver ions turn to silver solid. And they're gaining electrons, so we put an electron over there, right at the edge. Right, and that is your two half equations. Okay, combining these two half equations, I'd have to multiply that one by 2. And I'd end up with something like 2Ag plus Aq goes plus nickel solid goes to 2 silver solid plus nickel 2 plus aqueous. Okay, so that's the full equation as well, if you needed to write that one out. Okay, couple of other things, observations that you're going to see. This silver is turning from silver aqueous to silver solid. So observations at the silver, you're going to see that the electrode of the cathode gets bigger, which is useful. And the observations at the nickel half cell is that the electrode is going to get smaller. right? Because the nickel solid is turning to nickel 2 plus. We've also got to check our standard reduction potential table for other observations. All right. Here, this part of the standard reduction potential table. The silver ions that are produced, consumed and turned into silver solid. What color are these silver ions? Well, they're not here, which means that they are colorless, so they're just going to become less colorless, which means they just stay colorless. However, these nickel solid turning into nickel 2 plus ions. What color are these nickel 2 plus ions? The nickel 2 plus ions are green, which means that this solution here, as the nickel turns into nickel 2 plus, is going to also become more green. What becomes more green? The solution becomes more green. Okay. The solution becomes more green. Okay. Now lastly, we're going to also work out, what are we going to work out? We just did that one. We're going to determine the voltage of the cell. The E cell is equal to the E of the oxidant subtract the E of the reductant. What are these E's? They are on the standard reduction potential table over here, the E volts. So we need to find the E volts of our oxidant. Which one's our oxidant? Our oxidant is here, top left. Subtract the E volts of our reductant, the nickel over here. So we're going to take the top value and subtract the bottom value from it. We're effectively, considering these are all in order, we're effectively finding the difference between these two particular values. So let's go work that out, write it out. The E of the cell is equal to the E of the oxidant, subtract the E of the reductant. Our oxidant is the silver, and the silver and the nickel is our reductant. The silver has an E value of 0.8, and we're subtracting the E value of the nickel, which happens to be negative 0.24. So we're subtracting negative 0.24, which then just happens to be 1.04 volts. Okay, so just remember we're subtracting, and sometimes when you subtract a negative, you get a positive, they become a positive, and that becomes 1.04 volts. Okay, so that's the things that you're going to need to know from a particular question. You'll be given, you've got a silver half cell and a nickel half cell. You need to work out the electron flow of ions, the half equations, the full equations, observations, and E volts for it. Let's go do the next particular example. So what's the next example? The next example is the chromium and the zinc half cell. So let's do that one. The chromium and the zinc half cell. So let's go draw these out. Electrodes, beakers, what was it? Chromium and zinc. Chromium, zinc. The chromium ion that you put inside here is 3 plus. The zinc ions are 2 plus. Right. And what's missing? A salt bridge. Alright. Now let's go find our things over here. Right. So now we're going to find the chromium and the zinc. So the chromium is here. Right. And the zinc is, oh, right underneath it. Right there. Okay. So here you've got the chromium and the zinc. So we've got to identify our oxidant and our reductant first. Remember, our oxidant is in our top left, and the reductant is on the bottom right. Okay, so oxidant is the Cr3+, and the zinc is our reductant. If this is the oxidant, it undergoes reduction, and this undergoes oxidation. Alright, if these undergo reduction and that undergoes oxidation, this is losing electrons, loss of electrons, and this is gain of electrons. So which way are the electrons flowing, clockwise or anti-clockwise? Losing it from here, going that way, so the electrons are flowing that way. Right. Now we've got to work out the direction of ion flow in the salt bridge. Okay, so just got to remember, this is the flow of electrons, this is getting more negative. If this is getting more negative, that's where the positive ions will be, because the whole point of the salt bridge is to equalize out the balance, the charges. So the positive ions go that way, and the negative ions go that way. All right. Now we've got to work out the two half equations. Okay. So the two half equations. So I know that the Cr3 plus is undergoing reduction. So the Cr3 plus is going to reduce into Cr solid. And don't forget the electrons. Okay. So remember, that's the oxidant. It's going to go in the forward direction, because oxidants go in the forward direction. And the reductant, here, the zinc, undergoes oxidation with 2 electrons there. Again, the reductant here goes backwards. Zinc goes to zinc 2 plus 2 electrons. So now I have my two half equations. If I wanted to put those together, I could, but I'm not going to. Right, let's go through some of the observations that you might see as well while we're here. Okay, so the observations at the chromium half cell. Let's have a think. Is this going to get bigger or smaller, the electrode? Oh no, wait, I haven't worked out which one's the anode, which one's the cathode. Okay, so which one's the anode, which one's the cathode? The anode is where oxidation occurs. So that means this one is the anode. It's because where oxidation occurs. This one is the cathode, because that's where reduction occurs. So observation at the chromium, which is the cathode, which is undergoing reduction. So this Cr3 plus is going to turn to Cr solid, which means that this cathode is going to get larger. Okay, so the Cr electrode, which is the cathode, gets larger. Right. What color is the Cr3 plus ion? I don't know. Let's go find out. Cr3 plus, it's deep green. So if it's deep green, if this is deep green and it's turning into solid, the concentration of this Cr3 plus is reducing. So therefore, the solution becomes less green. But what about at the zinc electrode? Here, the zinc solid is turning into zinc aqueous. The zinc solid turning into zinc aqueous, which means that this anode, the zinc electrode, the anode is getting smaller. What color are zinc ions? Zinc ions, they're not here. See, they're not here. If they're not there, therefore they are colorless, so it's just becoming more colorless, which means you can't really see it. Right. So those are your observations for this particular, or these two half cells. All right, let's work out the E voltage of it. The E volts of the cell is equal to the E of the oxidant, subtract the E of the reductant. Which one's your oxidant? It's over here, the Cr3 plus. So E of the Cr, subtract the E of the Zn. Right. Okay. E of your Cr is negative 0.74 and negative 0.76 for the zinc. Okay, so 0.74 subtract negative 0.76. What mistake have I done there? Forgotten to put the negative on the chromium. So make sure that you do not forget to put negative signs where they should be. Negative 0.74 subtract negative 0.76 equals 0.02 volts. You should always get a positive number when you're doing this on a galvanic cell. Always on a galvanic cell. Right? On other cells, not so much. But now let's go on to the next example. Okay, the next example is what? Magnesium and cobalt half cell. Alright. So, magnesium and cobalt. Magnesium, cobalt. Okay. The magnesium is a 2+ ion. We need a salt bridge. The cobalt is a 2+ ion as well. But just in case you didn't know, it's right here, cobalt going into 2+ ions. Alright, so there's our two half cells. Now we're going to identify the reactants on the standard reduction potential table. So we just saw cobalt, it's here. And magnesium is where? Here. Okay, so top left, bottom right. This is our oxidant. This is our reductant. These are the two reactions that are going to occur. So the cobalt 2+ is the oxidant, and the Mg solid is the reductant. Alright, so we got an oxidant and a reductant. So we know that this is going to be the reduction reaction. This is going to be the oxidation reaction. This is going to be then the gain of electrons. And this is going to be the loss of electrons. You're losing them from here, and they're going to flow to here for these to gain it. Therefore, the electron flow is that way, which happens to be clockwise. Okay, now we're going to go for the ion flow. If this is the way that the electrons are flowing to that side as well are the positive ions. And the negative ions are going in the opposite directions of the electrons. They're going to where the electrons were. They're over there. Alright. Now we're going to identify which one's the anode and which one's the cathode. The anode is the one where what occurs? Oxidation occurs. So therefore this is the anode. And this is the cathode. Right, we've got anode and cathode, all good. Alright, now we're going to work out the two half equations. The Mg is the reductant, it undergoes oxidation. So the Mg is going to turn into Mg2+. It's oxidation. Okay, remember, the Mg goes to the Mg2+. This is the reductant, it goes backwards here. So I got some electrons here. And the cobalt goes from cobalt 2+ to cobalt solid, and some electrons over here. Okay, don't forget your states. Now let's have a look at some of the observations. So observations at the magnesium. Let's have a think. The magnesium solid is turning into magnesium ions. So therefore the magnesium solid electrode, or the anode, gets smaller. What color are magnesium ions? The magnesium ions aren't there. Therefore, no change in the color of the solution. At the cobalt, the cobalt ions are turning into cobalt solid. So therefore, this cathode is getting bigger. The cathode gets bigger. Alright, let's go check what color are the cobalt ions. Cobalt, here we go. They're pink. They're colorful. So therefore, is the solution going to get more pink or less pink? Let's have a think. Your ions are turning into solid. So therefore there are now less ions over time, which means that it's going to become, solution becomes less pink. Right? Then finally we need to work out the E volts. The E of the cell is equal to the E of the oxidant, subtract the E of the reductant. In this case, it's the oxidant is the CO and the reductant is the Mg. So what is the E of the CO? Here it is, negative 0.28. And what's it for the Mg? Negative 2.36. So negative 0.28 subtract 2.36. Okay, what have I done wrong there? I've forgotten the negative here. And that there. Alright. And so that difference is something like calculators. $2.64. No, that ain't right. Mr. Lim forgot to type in a negative value. Always remember negative values on calculators. Otherwise you're going to get things wrong. Just a quick question. How did I know that 0.25 whatever was incorrect? So I remember that the E voltage is of E of the cell is going to be the difference between these two values. All right? The difference between these two values can't be more than 2.36 because this is negative 2.23. And so I know on a number line that the difference between these is not going to be greater than 2.36. That's how I knew that 2.5 whatever was not right. Okay, so you've got to use a little bit of thinking to pick out when you make mistakes. Alright, so 2.8 volts, 2.08 volts. Alright, let's go look at the next example. What's the next example? Chlorine gas half cell and the acid half cell. Okay, so chlorine gas. What am I doing? Chlorine gas. Now this one's going to look a little bit different because you've got to pump in chlorine gas. So this is how you draw the gas half cell. Alright, what happens is that gas goes in here, and in this case it's Cl2, oops, Cl2, gas goes in there. Alright, this here is an inert electrode, and I've got Cl minus ions in here. Okay, so this is general mechanisms of mechanics of a galvanic cell. You should be able to know what to draw when you're drawing a gaseous half cell. Okay. On the other side is another gas half cell. A much fatter gas test tube now. Okay. Again, gas in here. It's H2 gas and H+. So this is called the acid half cell. So if it said something like it's putting it in sulfuric acid or nitric acid or hydrochloric acid, this would be one possible thing that can also be reacting. So it's got the acid, the hydrogen ions here and the hydrogen gas here. Okay, so this is also known as the hydrogen gas, the standard half cell as well. Right, what's missing? The salt bridge. Right, so now let's go work out all this stuff. Okay, again, this is also an inert electrode. What are some possibilities? C, graphite, and possibly platinum. Okay, so let's have a look. Here we have the acid half cell, here. Right, and where's the chlorine half cell? All the way up here. Okay, so we have chlorine gas as our oxidant and hydrogen gas as our reductant. How useful. Alright, so chlorine and hydrogen gas here. Okay, so chlorine gas is our oxidant, hydrogen gas is our reductant. This undergoes reduction to gain in electrons. This undergoes oxidation, which is a loss of electrons. This is losing them, this is gaining them. We're going to go this way. Alright? So, now we have to identify the anode and the cathode, and also the direction of the electron of the ion flow. So, if the electrons are going that way, what else is going that way? The positive ions. And the negative ions are going in the opposite direction. The anode is always where what occurs? Oxidation. So this here is the anode, and this thing here is the cathode. Make sure that you are labeling that very specifically. Right. Now we can get on to the half equations. So the half equations for the reduction, which is this one here, the oxidant undergoes reduction, which goes forward. So Cl2 goes to 2Cl minus. Cl2 plus 2 electrons go to Cl minus, 2 of them, AQs, gas. Right, and the other one, the hydrogen gas, goes to hydrogen ions, goes to hydrogen ions, and 2 electrons over here. Alright. What are some observations that we're going to see? Well, let's have a look. Observations at the Cl. Now, when you bubble chlorine gas into water, you'll form chlorine water, which is chlorine in aqueous solution is pale yellow. Okay, so when you bubble this chlorine gas in, it's going to make this water turn pale yellow. However, this particular reaction is going to occur, and so this pale yellow solution turns more pale. Why? Because this Cl minus ions are colorless, and therefore you're going to have this pale yellow solution because it's the chlorine gas is being bubbled in, and every time it gains electrons it's going to become more colorless, and therefore it's going to become more pale. Right, over here at the hydrogen half cell, you're going to have hydrogen gas turning into H plus ions, which you know you can't see, but if you were, you could also say that the pH increases. That is technically an observation. Okay, so those are some observations. All right, and then finally, let's go work out the E voltage. E volts is equal to the E of the oxidant, subtract the E of the reductant. What's the oxidant? It's the Cl2, subtract the E of the reductant, which is the H2, which happens to be 1.36, subtract 0. I don't need a calculator for that. 1.36 volts. Alright, so that's how you do and work out a whole bunch of stuff for different different galvanic cells. Right, I'm going to leave you to do the bromine half cell and the gold half cell and the copper half cell and the iron 2, iron 3 half cell. This is if a inert electrode where you've got the iron 2 and iron 3. One thing to note about this one is iron, I'll show you on this camera, iron is in multiple places in this standard reduction potential table. Okay, iron is here, and iron is also here. So really read what you've got. In the question, or that example there, we've got copper and iron 2, iron 3 half cell. The iron 2, iron 3 half cell is the one here at the top, not the one at the bottom. Okay, so make sure that you are picking the right half cell over here to use. Alright, so you have to go at those ones and see how you go.